Okay, so that's that. So let's go ahead and get into this material. And we showed you this picture last time. This is the simplified view of the architecture of an AVR microcontroller. And we're focusing on the IO port, okay? Now, just to make it clear, when we say IO port, like everything we're doing in the class from here on out, we're talking about a combination of hardware and software. So the hardware here refers to these pins, right? The actual pins that, pins on a chip or sockets into which we can put wires on the Arduino Uno board, which are wired to the pins on the chip. And we can cause those pins to go high or low. High is 5 volts and low is 0 volts. Or we can read them to see if they are high or low. And that's how we'll use those. It's one of the key ways we interact with the outside world. Okay, so let's see. There's a question about zooming. I guess if you are zooming, just make sure that you are muted. That's all. Okay, so 2 parts about these I/O ports. They're the actual physical pins and what they're connected to, and then there's the software. And what's relevant there are some registers that we have to communicate with. Registers are just special memory locations that are associated with these ports. And all we're going to be doing is we're writing values to these registers, or we're reading from them, and that's how we'll control the ports and read from them. Okay. Okay, just to remind you here, something we looked at last week. What we're programming is this chip itself. Okay, and then you have these. Let me just label the ports for you. This is port B. You can see PB1 through PB5. There's also PB6 and PB7. You have to kind of chase the pins around on the chip to find them all. That's port B. Port C then is up here. You have 0 through 5. And then you also have 6. Okay, so port B has 8 pins associated with it. This is an 8-bit machine, and it's based on an 8-bit byte. So the registers are 8 bits wide. So you'll notice that port B has all 8 pins associated with it, 0 through 7. In reality, we're only going to be using 5 of. Let's see. I'm missing. Oh, here's PB0. In reality, we're only going to be using 6 of these because these 2 here are occupied on pins 9 and 10 with the external crystal, the 16 megahertz crystal on this chip. So, when you look at this drawing that I'm marking up, what you can see is for each pin serves multiple purposes. So let's take this pin right here, pin number 28. That pin is PC5, so that's port C pin 5. We'll talk about that in more detail. It's also ADC pin 5. It's also SCL, and it's PC int 13. It can be configured for all of these purposes. So these various pins do multiple things. Right now, we're focusing on their use for general purpose input output. So we have port B, port C, and there's also port D, 0 through 4 here, and then 5, 6, 7 here. Okay, so we just sort of chase them around. All of that is also represented over here on the Arduino Uno side, right? And they're actually grouped a little more easily for us on the Arduino Uno. There's 0 through 7 there. All right, so that just corresponds to these. So you stick a wire in those, and you're connecting to port D, pins 0 through 7. Okay, and then we have PB0 through PB5. And you'll notice that on the Arduino, you don't have access to 6 and 7, PB 6 and 7. It's because they're taken up by that crystal right there. Okay, and then you also have port C, pins 0 through 5 here, right? So this is how we would access all those. And I'll show you examples where we're connecting LEDs and things to those. So that's the physical part of the ports. And now let's talk about the software side and the registers. How do we configure these ports? How do we make the pins on these ports go high or low? How do we hook up something on the outside to these ports? And how do we tell the microcontroller that we want to use these ports, either to read a value from the outside or to write a value? Well, this slide gets at the memory structure associated with these ports. Each of these ports, port B, port C, port D, each of them has 3 8-bit memory registers associated with them. Okay. So let's take a look down here at port D, right? You've got the physical pins there, and then you have 3 memory registers that you have to deal with to configure this port, to make the port behave the way you want. Okay, and so you have one of the registers is the data direction register, and you use that to tell the port whether you want these various pins to be input pins or output pins. Input pins meaning you're reading something from the outside world. Output pins mean you want to use them to control something in the outside world. So there's the data direction register. There's also the port D register and the pin D register, okay? And so up here on the left is sort of a shorthand for this. We have, for each port, there's a data direction register. And just so you'll know, this shorthand language, when we write DDRX, that means we're referring to all 3 of these, right? There's DDRB, DDRC, DDRD, the data direction register for each port, okay? There's also a data register, one for each port, and there's also an input pins register, okay? So we're going to look at this in detail, but roughly what happens is you first decide whether you want one of these pins in a port to be an input pin or an output pin, and you set that with the data direction register, right? You set the direction, input or output. If you want it as an output pin, then you're just going to put a value in the port data register, and that'll cause whatever value you put there in software to appear on that pin. If you put a 1 there, you'll get a 5 volts on that pin. If you put a 0 in that register, you'll get 0 volts on that pin. If you've configured them as inputs, then you'll be able to read those values using the input pin register. Okay, so the game here is you just set, using the DDR, you set the pins as being input and output, and then if they're outputs, you just write data to the port register, the data register, and if you want to read values, you're going to read those on the input pins register. Right? There's a little more to it than that, but we'll show you that. I'm going to show you that same thing in a number of different ways. Okay, so again, each of these registers has associated with it 3 ports that you have to deal with when you want to interact with the physical world. So let me just show you some examples here. If I use this command, DDRB equals 0xFF, okay? What I'm doing there is I'm setting, by the way, FF, that's hexadecimal. And you know, F, if you convert that to binary, F is 1111. So FF would be 1, this would be the same here as, would be 1, 1, 1, 1, 1, 1, 1, 1. The reason why it's so messy is I've got a right-handed mouse and I'm left-handed here. With a command like this, what we're doing is we're saying all of the pins, all 8 pins in data direction register B are 1. That's making them all output pins. So what that command would do is it would take all of these and it would cause them and configure them as output pins. So you could use those to turn on and off LEDs, or you could use those to make noise from a little piezo speaker, turn on a coffee pot, launch a rocket, right? Whatever you wanted to do with those, with those pins. This line here, I'm setting those all to 0s instead of 1s. So if I set the data direction register pins to all 0, we're configuring them all as input pins instead. On the next slide, I'm going to show you the hardware that actually causes this to happen. Okay, if I use this command here, port B equals 0, what I'm doing is I'm setting all those pins low. right? If I had configured them as output pins and then I set them all low, then I'd have 0 volts at each pin. If instead of 0x00, I use 0xFF, I'd be setting them all high, okay? And if I had some value in between 0, 0, and FF, I'd be setting them low or high, depending on the value that I assign here, okay? Okay, so Benjamin asked a great question. How do we only set 1 or 2 pins high instead of setting them all? We're going to get to that. We have to introduce bit level manipulation, or what some people call bit twiddling. We'll get to that. Okay, okay, if I wanted to read some pins, right, then pin C is the register that captures the actual value of those pins. So what I would do is I would have some variable, let's call it input value, and I would set that equal to pin C. Then variable input value would now have the value of all those pins. Okay, this is the hardware that actually makes this happen. This top drawing is quite complicated, and you have to really stare at that for a long time to be able to make sense of it. But we're going to work with a more simplified version. But I just want you to get the basic idea here. Notice in the circuitry that you see here applies to each and every pin. So for port B, which has 8 pins, you would have this whole thing replicated 8 times. So all of the circuitry exists for each and every pin. Okay, what are some things you may recognize? You'll see this. This is a flip-flop, right? This is a D-type flip-flop. Here's another D-type flip-flop, okay? And here you have sort of a combination of D-type flip-flops, all right? Notice the directions of these. D is input, Q is output. So this is sort of a flip-flop going in that direction. This one is sort of also going in that direction. And this one down here is going in that direction, okay? And so the purpose of all this is, well, you want to have some data that you want to put on this pin if you want to make it an output pin. So information that's going to come from a data bus is going to get latched into that flip-flop and then is going to be made available to that pin, right? Or you want to have, if you're reading it, you want to have input data from the outside world get latched into there and then made available to the processor. This flip-flop here controls some amplifiers, and it establishes whether they're going to be input or output pins. Now, how does this all work? Do we have to get in and trace all these wires? We're not going to do that. Instead, sort of let's abstract it away, right? And when I say abstract it away, what do I mean? You know, if you are ever reading a document, or if you're writing a document, and you'll write some of these when you get to junior writing, but you know, if you read a technical paper, the paper itself might be 6 pages, 10 type pages, but there's also an abstract, right? Abstract is just a few sentences, and it says, this is what this paper is about. If you want all the details, go read them. If you just want to get the gist, read the abstract. And the abstract allows you to hide the rest of the details. This picture down here, you can think about that as an abstract. What it does is it hides all the details, but it conveys the essence of that more complicated picture. Okay, and so the idea here is, first we're going to set the DDR pin associated with a particular register. We're going to set that high or low, and we want to be able to do this for every single bit in every single register. Set them as being input or output, and then if you set that to be set it high, then you'll be able to take data from memory and pass that to that pin, and it'll control the outside world, you know, by turning something on or off. Or you set the DDR low, and it'll allow you to read values on those pins. So this is how you can use the same pin as both an input or an output pin, okay? So we call this IO, input and output. More generally, we call it GPIO, general purpose input output, okay? So our chip, the Atmega 328P, has 23 of these general purpose input output pins. They're in ports B, C, and D, and we're getting at sort of the structure behind each one, all right? So think about, if we just look at this pin right here, right, pin PC5, it's got this sort of collection of hardware, right, associated with that pin. And so what we have to do is we have to tell that data direction register whether we want that bit to be high or low, and that'll set this particular pin as an input or output pin. Then we also, if we want it to be an output pin, we have to put a 1 or a 0 here. And then if it's an input pin, we want to be able to read that value there. Okay, so we're simultaneously thinking about the hardware and the software, right? And when we say software here, what I really mean is we want to be able to read from registers or write to registers, right? Okay. So this was the piece of code that I showed you on Monday that we used to blink an LED. Whoops. Okay, now let me see. I have a question here that has come up in the chat. Let me get myself caught up in the questions here. Okay, does input value read all the pins at the same time, or can you read one pin at a time? So the compilers that we're using to take C code and turn that into machine code will only allow you to access these registers a byte at a time. If you wrote assembly language, you would be able to access each individual bit. But what we'll do is when we write a value to port A, port B, or port C, it's going to configure all of the bits in there. Likewise, if we read pin A, pin B, or pin C, it'll simultaneously read all the values from those pins. So I'm going to show you, though, how we get into it. How do we actually twiddle individual bits in there, even though we're reading and writing to all bits at once? Okay. Okay. Question is, do we have to worry about affecting the non-GPIO pins when we're using pins that have other functions? And the answer is sometimes you do. So for example, Alexander asked a question, since PB6 and PB7 are connected to a crystal, what happens if we write to them, right? Will that foul us up? And generally, you have to be aware of the potential for conflict. And I'm going to show you some cases as we get into this. What happens if you are writing to some pins that are also being used because they have multiple functions and you're using those other functions? We'll look at that as time goes on. Okay, so back to this code. How does this code that we looked at on Monday, how does it cause an LED to blink? Right. Well, first of all, let's take a look at what we can sort of understand right now. There's DDR-B, so we're talking to data direction register B, and we're sending it this. Now you don't know what that means yet, right? What that will actually do is it'll be a pattern 0. I gotta get a left-handed mouse. 8. Let's see, 7, 6, 5. 4, 3, 2, 1, and 0. That's the binary equivalent of 1 less than PB5. This less than is actually a left shift operator. And what you're doing is you're taking a single bit, a single high bit, and you're moving it to the left 5 positions. We'll get into that. But I just wanted you to see what this command is doing is it's putting a 1 in the position here, PB5, corresponding to bit position 5 in register B. So what that is doing is it's saying make that one pin an output pin and all the rest are going to be input pins. Then we get down here and notice we're sending to port B, we're sending the same instruction. It's the same value, 1 left shift 5. What that's doing is it's making the bit PB5 go high. Down here, it's sending the opposite of that. It's making that pin go low. The result of this is it makes that pin go high. First we set pin B5 as an output pin. Then we set it high, We wait a little while, we set it low, we wait a little while and repeat. And that's what was causing our LED to blink on and off. Now, how does the compiler know what DDRB is? And how does it know what port B is? I mean, how does it just know that? Well, let me show you a little more detail here. I want to go to the next slide. Well, first, I want you to notice this. I want you to notice that I have this include statement here. Include AVR IO.H. So what that statement is going to do is it's going to reach into the library that comes with the AVR GCC toolchain installation. It's going to reach into that library. It's going to find the file AVR.io.h, and it's going to copy the entire contents of that file into the program before it compiles. That's a preprocessor directive. So that's the very first thing that will happen as you start to compile. It sees this pound sign, right? The compiler says, okay, I get this is a preprocessor directive. I want to go and copy the entire contents of that file into this program. All right, now let's see what that looks like. This is just a small piece of that file, io.h. If you're interested, this is where you can find it. You have to sort of go hunting around to try to find it. You don't necessarily need to, in fact, you don't need to worry about what's on this slide, but I just want to show it to you for your information. Okay, someone has asked, does the full library take up space in the program? In this case, what's happening is it's a header file that's being copied in. And a header file doesn't actually have any C statements. What it has is a bunch of macros, a bunch of defined statements, which don't take up any memory. And I'll show you specifically what I mean. So you can see that this file, but all this text gets included right on top of your program. And you can see, let's see. There's a statement that looks like this, right? What it's basically doing is it's determining whether or not this file, this code is intended for the Atmega 328P chip or some other chip. Now, you may remember on Monday when we were setting up the compile command, we specified that our target microcontroller was an Atmega 328P. What happens is this file actually says, is this intended for a 328P or some other chip? If it decides it's intended for the 328P, it will then go in and it will include this file. This is called the port pins file for a 328P chip. Now, I realize I'm way down in the weeds here, but this is the point I wanted to tell you. I wanted to get to you. You see this thing here? This is the actual memory register address for port B. This is the actual memory register address for data direction register B, okay, and so forth, okay? The first one corresponds to pin B, next one is data direction register B, and this one is port B. So these are the actual memory addresses for these three registers, pin B, port B, and data direction register B. So the actual code has to do reads and writes to these registers. We don't have to ever concern ourselves with what these registers are, because what this file is it's coming up with nicknames for all these by creating these symbolic constants. So what it does is it defines pin B as this sort of funky address. It copies that into the top of the program. The result of that is every single time, it's doing these kinds of defined statements, right? So the compiler first copies all that stuff in there. It has these defined statements. Then every time it sees DDRB, it replaces that with this address, right? Every time it sees port B, it goes and replaces it with this address. Okay, so DDRB and port B, they're just nicknames. You can think about them as macro replacements or symbolic constants. We've used these before in our programs. It makes it really convenient for us to program with these because we don't have to worry about the actual numbers, the hex or memory address locations. That gets taken care of for us. So that's the purpose of this include statement. It gives definition to these things, and we had to tell it in the compilation process. We have to tell the compiler which processor we want. This command will then go ahead and it'll pull in the right header file with all these definitions, matching them up to the memory locations. Okay, so that's what's going on. So to Benjamin's question, does this take up space in our program? No, none of this takes up any memory space because these are all preprocessor directives which don't take up memory space. On the other hand, there are many libraries that you would want to include that do take up memory space, and we'll be looking at that later on. Okay, so just to kind of summarize what we've been talking about so far, we've got this complicated view here, and we've got our simplified view here. That's the hardware. And I want to kind of summarize the behavior at the individual pin level with these tables. So first, if we want a pin to be an output pin, right? I mean, we want to take data and blast it right out through all this so it shows up at that pin, right? And the way we do that is we set the DDR register for that pin high, all right? We set that equal to 1. And then when we write to the port register, all right, we can write a 0, which is going to cause that output to be 0 volts, or we can set it to be 1, and the output's going to be 5. When we set DDR to be 0 as input pins, the picture is a little more complicated because it has what's called a high impedance value, or it has a pull-up value. We'll get to that in a bit. I want to sort of set that aside right now. And what I want to do is just show you some examples where we dig into this and set individual pins. Okay, so just an example right now. Let's suppose I want to write a program that sets all of the pins on port D to high. Okay, for all of them. So all of these, I want to write a program segment that makes all of those high. So I could go and I could get a multimeter and I could measure them all. I'd get 5 volts. Or I could hook them up to LEDs and they'd all glow. Okay, so in other words, first thing I have to do is I have to set, I want all those pins to be 5 volts output. So first I have to set data direction register B. I have to set all those bits equal to 1. And then I have to make all those pins high. This is what I want to achieve. So I have to put these values into those registers. So here's my program segment. I could just do this. DDRB equals, and I could write it in binary if I want, right? When I use this preface 0B, it means I'm writing a number in binary. And here I'm just putting all 1s, right? That's going to cause this to happen. That makes them all output pins. Then the actual value that I write, all 1s, it's going to cause this to happen, okay? Now, this block is another, I can write the same thing, but instead of in binary, I write it in hexadecimal. And you're going to get really good at converting between binary and hex. All you do is you take the lower 4 bits, the lower nibble, that corresponds to that F. And then well, actually, it's this one here. Right, the lower 4 bits correspond to 1 hex number, and then the upper 4 bits, the upper nibble, correspond to the other number. And you'll get really good, and you'll be able to do this in your sleep. So what you'll find is writing things out in binary is cumbersome because you have so many 1s and 0s, and it's hard to even count how many 1s and 0s. Just try to count how many 1s you have there, and it can be challenging. Whereas when you write it as 0xFF, once you get the hang of that, you'll say, we're making all these high. You could also do it in decimal, but it's much harder to convert between binary and decimal. You can't do that automatically. That's why I write here, it's more difficult. So what you'll find is you're going to get very comfortable. You'll think about what's the pattern I want? What am I trying to achieve here? You'll be able to do that in hex most easily. Okay, another example here. Let's make a complete program now, right? Let's make a complete program that's going to make all of these output pins. So I want all of the pins in port D to be output. So it's all of these. I want to make them all output pins. Okay. But I want to set 0 through 3 low and 4 through 7 high. Okay, so I want these to be low. I want those to be 0. And I want these to be high. Okay, so how do we do that? Well, this is what I want. I want to set all of the bits in DDR B. This is port B. I'm going to make all those 1, so they'll all be outputs. And then I'm going to put 1s in the upper nibble and 0s in the lower nibble, and that'll configure those pins as being high or low. So here's our code, right? DDRD, we just give it 0xFF. We'll make all those pins output. And then here, 0xF0, 0xF0, that's F, and that's 0, okay? F and 0, okay? So if I wrote this code, what it's going to do is, the first thing that'll happen is I'm going to set the data direction register, make them all outputs. Then I'm going to set the upper ones high, the lower ones 0. Then I get into a while loop, and I'll just sit there forever. That's what this program will do. When we flash this code, it'll set those pins, and then it'll just sit. It'll just sit waiting forever, right? Waiting until I power down, because that's what that loop will do. While 1 semicolon, right? You know, while 1 is always true, so it'll just sit there forever. So let's go ahead and make a program to do this. This is the code. Okay, this is a code in Visual Studio Code of the same thing I had here. Okay, so there's the code, and I'm going to compile this, and I'm going to flash it, and to do that, I'm going to use the make file. We talked about that on Monday. Okay, we've got a question. How do we set analog inputs to read? There is an analog to digital converter, and port C does double duty. The pins on port C can be used for GPIO like we're doing here, or as analog input. We're going to get to that in a couple weeks. And the analog input, you can think about the analog input as one peripheral, and you can think about the GPIO as another peripheral. And the way we're going to attack this is we're going to look at all of the different peripherals in turn. GPIO, analog to digital converter, the UART, we're going to look at the timers, we're going to look at the interrupts, right? We're going to, as time goes by, we're going to learn about all the different peripherals. Okay, the make file here, here it is. I run it. Okay, let me walk you through what's going on in here. This is now this is on my Mac using terminal. So I wanted to. I'm calling this. I'm going to back up a slide. Right. I'm calling this example 1, and that's because it's example 1 in your book. That's where it comes from. It's based on that. Okay. So I wanted to create a project folder called example 1. So I made that here. Okay. And then I copied the make file. Previously I have a make file in Blink, which I showed you last week. I just copied that make file into this folder here. Then I moved into that folder with the change directory. I opened up Visual Studio Code. Okay. And in the make file, I'm going to go to the next slide, and it's going to show the make file. And if you haven't looked at this yet, you'll encounter this. This make file is up on the week 4 tab of Moodle. You'll need to become familiar with this a little bit, but you just have to modify these 2 lines. You have to modify the name of the source code file that you're using, and you also have to make sure that you have the correct port address that the Arduino is connected to. Okay. Question, will these commands in terminal translate to command prompt? They're almost the same. The commands, most of the commands in terminal, in Mac OS terminal, are the same as Windows 10 command prompt. But I will publish a document. I'll make a note here. Terminal. Okay, so to Benjamin's question about the difference between the commands for command line for Mac OS and terminal. I'll publish a document later today, so you'll have the translation between those. But these are the two things in the make file you have to change. And so I want to, we know the name of the source file. It's example1 main.c. The serial port here, what I'm doing is this is how we would do it in a Mac. I type this command, list devices that begin with TTY, and I get this result here. This tells me the serial port that my Arduino Uno is connected to. So then I took that value and I just typed that in right here. Okay. This will make more sense to you the first time you do it. Okay. Then all I did is I typed make. That compiled the code. It sort of did all this stuff for us. It just does all this. Then I typed make flash, and it uploaded the code to my Arduino. Now, how are we going to know if this code is doing anything, right? What we did is we set some pins high and we set some pins low. What I'm going to do is I'm going to connect some LEDs to those pins. So I'm going to show you a circuit here where it has 4 LEDs connected to those pins. And so I just pulled the pieces that I need from the kit, and then I just built them here. And so what I was doing is I was setting the upper nibble of port B, which corresponds to pins 4, 5, 6, and 7. I connected those with some resistors to some LEDs on the breadboard, and they're glowing, right? So that code, this is what it does. It just turns on those LEDs. So it's not doing anything too special. Let's make it more interesting, though. Let's create code that's going to alternately blink 2 groups of LEDs. So we want to alternately blink LEDs on the upper and lower 4 bits of port D forever, with a 1/4 second delay in between. So just take a minute to digest that. We want to alternately blink LEDs on the upper and lower 4 bits. So I want to turn on a set of LEDs on the lower 4 bits. I want to wait a 1/4 second and then turn on some LEDs on the upper 4 bits. So it's 4 LEDs, 4 LEDs, and then sets of 4 LEDs that are flashing on and off. Okay, so how are we going to do it? We're going to first set port D to all output. We're going to use all pins as output. And then here, what I'm going to do with this command is I'm going to cause the lower 4 bits to be low and the upper 4 bits to be high, because I'm giving it an F0, right? F0, right? That's not FO, it's F0, right? And F corresponds to 1, 1, 1, 1, and 0 corresponds to 0, 0, 0, 0. Okay, so that's the value that we wrote there. And so these are all high. I'm going to put a set of LEDs on those, and they'll be on, and these will be off. Okay, we have a little bit of a delay, 250 milliseconds. And then I'm going to give port D the command, the value 0F. So it was F0, now it's 0F. And so I'm just swapping them. Okay. Here's the command. This is just the same code as I just wrote. This is just here typed into Visual Studio Code. Okay, there's my circuit, right? So now I have all eight pins here from port Z are connected to resistors and then to LEDs. And I put some green LEDs for the lower 4 bits and red LEDs for the upper bits. And when we run it, all right, it's just toggling back and forth, right? A 1/4 second on each. Okay, so you see that what we're doing is we're gradually working our way up from, first let's blink an LED, then how do we just turn on some LEDs? All right, how do we do more interesting things? And we're just going to keep doing this. We're going to just keep looking at how we can manipulate these bits in different groups, different combinations, different loops. We'll put some switches into the mix so that we can have something that we can use to measure what's happening in the external world. We'll configure a switch so that we have some input pins that can be high or low, right? And that'll sort of complete the general purpose input and output, okay? Now, to a question that was asked earlier, how do we actually talk to one individual bit? Because in the examples I've shown so far, right? Let me go back. I'm going to go back to the code here, right? We're with a line like this, we are setting a value for every single bit in that register. Port D is an 8-bit register, and I'm giving it an 8-bit value, right? 0xF0 is giving it, 11110000. So we have to actually assign a value to each and every bit. So how do we use that to just control one bit? That's the question we want to get to, right? So here, the problem here is that our compiler, it only supports bite-sized programming, right? We're not able to write to an individual bit in a register. We don't have access to it. We can only access the entire bit at a time. I'm sorry, the entire byte at a time, right? When we write to this register, we have to give it a value that applies to the entire byte, all 8 bits. So how do we control just one bit and not the others? Well, suppose I want to toggle an LED on pin BB5. Toggle means on, off, on, off, on, off, on, off, right? Toggle, back and forth. Okay, so here's some code that would toggle an LED on pin B5. I'm going to make all those pins output. I'm going to set them all high, and I'm going to set them all low. All right, so what it's doing here is I'm setting all those pins as output, and then I'm making them all high, and then I'm making them all low. Okay, now, am I toggling an LED on pin PB5? Yes, I am, right? To find PB5, this is 0, 1, 2, 3, 4, and 5. So PB5 is going between 1 and 0, right? So I am toggling it, right? So if I had an LED on there, it would flash, so it's being toggled. But what we want to know is, how do we just talk to one of those bits, right? Since this code is turning all those bits high or all those bits low, we would consider this a brute force approach, okay? Someone wants to know, is there a case when you would change the DDR register while inside the loop? Yeah, there are all kinds of use cases for doing things in lots of different ways. And it depends on the application. Okay, let me try to do this a different way. Suppose I want to only toggle the, and by the way, the reason why I'm using pin PB5, that's the built-in LED on the Arduino. The Arduino Uno has a built-in LED on the board. That's what we were programming on Monday. It corresponds to Arduino pin 13 or at Mega pin B5. But if I only want to toggle that, I don't want to toggle all the rest of them. How can I do it? Can I do this? Can I, instead of writing in hex, can I write in binary, say, right? Well, here with this line here, I'm making pin B5 an output. All of the others are input. And then with this line here, I'm setting pin PB5 high, but I'm setting all the other ones low. And now I'm setting PB5 low. Okay. So what this code is accomplishing is shown over here. I am still toggling this one high or low, but I'm making all the other ones low, right? So it's still brute force because we're still programming all the pins at once. Okay. Question: does writing it in binary take up more memory? No, it doesn't. By the time, I mean, the compiler is going to see 0xFF, or it'll see 0B, 11111111, or it'll see the number 255, and they're all going to get compiled down to the same value. Okay. So how do we get to one bit at a time? That's what we want to get at, right? How do we do that? How do we configure individual bits? And when we say configure individual bits, we mean, just to get some of the language, we want to set a bit, right? If I say set it, that means make it high. Clear it means make it low, or toggle it, meaning if it's high, make it low. If it's low, make it high. So set, clear, set, clear. Right? How do we do that without impacting the other pins in a register? All right, we have to introduce bitwise logical operations. Previously, we looked at some logical operations, but they operated on objects, meaning like variables, numbers, and they were occupying bytes or multiple bytes at a time. We want to look at bitwise logical operators. And this is where we're going. So a statement like this, you won't understand this yet, but what this is going to do is it's going to set bit 5 of data direction register B high, and it'll have no impact on the other bits. Okay. Now a clue here, that is an OR statement there. That represents an OR. Okay. The next line here is going to set PB5. That's bit 5 of port B. It's going to set that high, no impact on the other bits. All right. Look at that piece of confection there. That's going to set PB5 low. That is going to toggle PB5, right? So this is how and then I'm going to just show you one more variation of this. I can take everything I've shown there, which you don't understand yet, and I can rewrite it this way, right? Instead of doing 1 left shift 5, I can also do this. And I'm just making use of the defined constant DDRB5, which is just equal to 5. Okay, so these all correspond sort of 1 to 1 here. But look at stuff like this. This is how the cool kids do this, right? We're going to learn how to use statements like this that will set one of these pins low and not touch any of the other pins. That's the key. So this is where we're going. Okay?
Professor, you have a question in the classroom?
Go ahead.
You technically use like addition rather than the core operator there if you want to set one of it. Set it high.
Okay, repeat the question, Dave?
You use addition, so plus equals instead of an or operator. If you added with the bit that you wanted to.
Yeah, the question is how do we do it, right? How do we get there, right? So it's going to take me about half a dozen slides to build up the sort of the theory and the background and the concepts that'll get to this. So just bear with me, and I'll show you how to get there. Okay. So just to compare this with the logical stuff that we've done already, right? Previously, last week we looked at these kinds of operators, right? And so they operated on what we call logical objects. So for example, if I were to have something like this, 4 greater than 5, right? And I ask, what is the value of 4 greater than 5? That's either a 1 or a 0. And so if I have 4 greater than 5 and 10, right? And I look at what's the value, what's the result of that expression? It would be 0. Because 4 greater than 5 is 0. 0 and 10 is 0. If I looked at 4 greater than 5 or 10, that would return a 1. If I looked at not 0, that would return a 1. But the point here is, when we do these kinds of things, they were working on logical objects. By that I mean this operation here, it's operating on the result of this and the result of this. It's not doing anything at bit level. It's dealing with the whole object, 4 greater than 5 or 10, right? It's dealing with that whole thing. I want to now introduce a new set of bitwise operators here. Okay, there's the symbol for them, right? We have and, or, we have exclusive or, and then we have complement. And what we're going to find is that they operate on individual bits. So if I take as an example, if I take this pattern of bits and I AND it with this pattern of bits, it's going to give us this result. And it's going to actually do that AND operation bit by bit. Or we can do an OR operation bit by bit. So I'll break that down for you in detail on the next slide. And so to get there, let's just sort of review from ECE 124 when you looked at logical Boolean operators and gates and things like that. Okay. Remember, you had an AND gate, you had an OR gate, you had an exclusive OR gate, and you may have been wondering, why would I ever use that? Or maybe you grew to love the exclusive OR gate, but we're going to be using it all the time. Okay, so up here we have a truth table. So I'm showing you all the possible permutations of the 2 bits for A and B, right? They could be 0, 0, 0, 1, 1, 0, or 1, 1. Now, here's A and B, right? A and B is only going to be 1 when both A and B are 1. We have the OR gate. A or B will be 1 when A is 1 or B is 1 or both. We had the exclusive OR gate, right? So A exclusive or B is 1 when A is 1 or B is 1, but not both, right? That's the exclusive or. It excludes the part where they're both 1. Then we also had an inverter, right? So if by inverting B, if B is 1, then the inverted B is 0, okay? So to take that information and do some bit by bit comparisons within bytes. So let's look at this first one here. All right, so we're going to take two bytes, this one here and this one here, and I'm going to AND them, and we're going to end up doing a bit by bit AND. Okay, so we'll start with the first one here. Right, 1 and 1 gives us 1. Okay, the next one, 1 and 1 gives us 1. 1 and 0 gives us 0. Right, and so forth. Right, go all the way down the line. So the rule here is that let's take this one. Right, if you take this and you AND it with a 1, you're going to get a 1. But if you take something and you AND it with a 0, you're going to get a 0. Okay, so now let's see what happens if we take a 0. Take a 0 and you AND it with 1. You get a 0. So think about these as sort of the starting values, right? If I start with a 1 and I AND it with a 1, I get back to 1. If I start with a 0 and I AND it with 1, I get back to 0. So if I AND something with a 1, I get back the original bit value. AND it with 1, I get back what I started with. AND it with 0, and I'm going to get 0 as a result. So this is something we have to sort of put into our toolkit. What we're driving toward is some bit level capability that will allow us to go in, mask out the other bits, and just decide whether we want to turn a particular bit in one of these registers high or low, or toggle it or something else. Okay, so that was the AND. Now let's look at these bitwise ORs. So let's assume we're kind of starting with these values, right? And then we're going to OR them with this. What happens? So I take my 0, I OR it with 0. Okay, I get back a 0. I take my 0, OR it with 1. I get back 1. Okay, take a 1, OR it with 0. I get a 1. All right, I go through all the combinations, and what we see is when we have something, if we OR it with 1, we get a 1. If we OR it with 0, we get the original value back. And so what these operators allow us to do are change individual bits. Right? If I ANDed something at a bit level with 1, I get back the original value. I AND it with 0, and I'm forcing that bit location to go to 0. Okay. Let's look at the exclusive OR. Okay. So assuming I'm starting with these top ones here, right? And suppose I take in this position here, I look at what happens if I exclusive OR that with a 1, I get a 0. If I had a 0 and I exclusive OR it with 1, I get a 1. Okay. If I had a 1, I exclusive OR that with 0, I get a 1. All right, so we collect all that into a rule. What's happening here? Well, what's interesting is here, I started out with a 1. Okay, I end up with a 1. There's no change. All right, here I started out with a 1. I start out with a 0. I end up with a 1. I'm toggling here. All right, and the rule is if I exclusive OR with 1, I'm toggling. Right, so that means if I had a 1, it becomes 0. If I had a 0, it becomes 1. If I exclusive OR with 0, I get back the original value. Right, so I know this is kind of dense, and I went through it kind of fast. But what you can see here is the capability for us to go through and set or clear or toggle individual values. And we can do that by judicious choice of this AND, OR, and exclusive OR combinations here. Okay, so, and I think I'm just going to show this, and then I'm going to let you go. Move this. Okay, so let's suppose we want to clear a bit, right? Let's suppose I have one bit that I want to clear, right? Like there's this bit right here, and suppose I want to force that to go to 0, right? Whoops, I picked the wrong one. I'm sorry. I meant this one here. if I want to force that to go to 0, right? What I could do is I could AND that with a bit pattern that has 1s in all locations except that one, right? Because if you AND something with a 1, you get back what you started with. If you AND it with 0, you're going to get back 0. So the result of this is it takes that 1, I'm ANDing it with 0, and I get a 0. This operation allows me to clear out the bit in position 5. This thing here is called a mask. It's called a bit mask. And by putting a 0 in that mask, I can zero out that bit position. So if you want to clear a bit, right, you want to cause just one bit out of the whole byte to go to 0, what you do is you AND it with a mask that has a 0 in that particular position, and that'll force that bit position to go to 0. That's how you clear a bit. How do you set a bit? We're going to use an OR mask. Okay, so let's look at this operation here. If I want to set this bit, what I could do is I could OR it with a 1, and that'll cause it to go high, right? And it won't impact the other bits. Okay, and this would be a mask that has a 1 in a particular position, and that would, by ORing sort of an input value or ORing an initial value with a mask that has a 1 in a particular position, we're setting that particular bit and not impacting the other bits. So that's the key to this thing, is when we do this business of bit level masking, we are able to set or clear an individual bit without impacting any of the other bits. That's the important thing. Okay, and then we can toggle using exclusive OR. Okay, so let me just look ahead here. All right, I'm going to leave it at this, and we're going to pick it up on Monday. We'll finish this up, and we'll talk about how to do inputs and use switches. You want to be starting on your homework. And by the way, I'm going to change the homework due date, and I'm going to change some of my office hours. The reason being, we have most of our support hours sort of at the beginning of the week. We don't have much toward the end of the week and weekends. And by having your homeworks due on Sunday night, we're not able to provide you with a lot of support. So I'm going to make the homeworks due on Wednesday or Thursday, right? That way, when you're working on it, for those of you who tend to wait till, inevitably sort of before to do, we'll have some hours for you. So I'll send a note out to everyone updating you on that. Okay, that's it for now.
We'll